next session on virtual labs. In this session, we are going to study the last experiment of Machine Dynamics and Mechanical Vibrations lab. The title of the experiment is Dynamic Vibration Absorber. The aim of the experiment is to understand the dynamic vibration absorber system as simplified single degree of freedom system and study its characteristics for different excitation frequency and amplitudes and masses. So we will be converting a dynamic vibration absorber into a single degree of freedom system, and then we are going to analyze by changing certain parameters like mass, stiffness, frequency, the force. Let's check the theory. There are certain learning objectives given. After completing this simulation experiment, one should be able to model a given real system to an equivalent simplified single degree of freedom system and reducing the vibration of the main system, adding an absorber system with suitable assumptions or idealizations. So after completing this experiment, you will learn how to convert a given problem into a single degree of freedom system, and you will be able to add an absorber such that the vibration caused in the main system is reduced. There will be certain assumptions and idealizations in this experiment. Determine the amplitude of vibration for both main and additional system. Tune a vibration absorber by varying dynamic system parameters. Study the response of the vibration absorber for different excitation frequency and amplitude. Now let's see what is a dynamic vibration absorber. When a structure is externally excited, it will have undesirable vibrations. The amplitude of vibration will be maximal when the system gets excited close to its natural frequency, and this can cause rapid catastrophic failure. This is talking about resonance. When your frequency of the body or the vibrating body suddenly matches one of the natural frequency of the body, it will show resonance and hence this kind of a catastrophic failure. Hence it becomes necessary to neutralize these vibrations. One of the methods for neutralizing these vibrations is by coupling a vibrating system to it so that the amplitude can be brought down to 0. So what you will do is you are going to add a vibration absorber such that it will bring down the vibration to 0. This kind of vibrating system is known as vibration absorber or dynamic vibration absorber. DVA is the abbreviation. DVA are used to control structural vibrations where it concentrates on neutralizing the amplitude of vibration at resonance. Some practical examples of dynamic vibration absorber are shown in the figure 1 and 2. So this is a dynamic vibration absorber in a steel stack, and this is a dynamic vibration absorber PCB. So you can see here there is an internal ring which acts as a vibration absorber in the PCB. To study the dynamic absorber system, a real system considered as main system is modeled as the equivalent single degree of freedom system, and it is excited by a harmonic excitation force F is F0 sin omega t. So you can see here the main system is shown as a single degree of freedom system. There is only one direction of motion. This mass is moving only along this x-axis, and K is the stiffness shown. It is excited by an external force which is of sine form. It's a harmonic motion. F is F0 sin omega t. The steady state response of the system is given by X is capital X sin omega t plus phi. Steady state amplitude of vibration of the proposed single degree of freedom system will be maximum at the resonance. So this is what we understand. To neutralize the effect at resonance, the main system couples with an absorber system. This coupling will suppress the amplitude of vibration of the main system. By the addition of absorber system, single degree of freedom analysis cannot hold. Hence, whole system should be considered 2 degree of freedom system. Now, if you are understanding that there is a main system as we have shown, and also there is an absorbing system which will consist of a mass and a spring, that's how you resolve everything. So if you have both of them, it cannot be shown as a single degree of freedom because this absorber will also have some effect on this main system. So this will now be modeled as a 2 degree of freedom system. So this is the free body diagram of vibration absorber system. You can see here M1. This is under the effect of K1 and K2 both. And M2 is only going to be acted upon by this K2. This is under the effect of K2. M1 is under the effect of K1 and K2 both. The free body diagram of the masses are shown in the figure 4. By application of Newton's second law of motion to each of the masses gives the equation of motion as m1 x1 double dot plus k1 x1 plus, for this body there is an effect of this spring 2 also. So this equation also comes into picture, k2 x1 minus x2. x1 is its own displacement and x2 is the displacement of mass 2. Hence it is x1 minus x2. And this will be equated to f naught sine omega t because the main system was excited by a harmonic force f naught sine omega t. Then we'll see the equation 2. It is m2 x2 double dot plus, when you talk about the mass 2, it is acted upon by this spring k2 and the displacement will be x2 minus x1 because we are talking about the body 2. Hence x2 will be shown first and then x1. This is the pattern of writing so that we are able to distinguish between the effect which is caused by these spring and masses. So when you talk about mass 1 and you're talking about K2, you will write x1 minus x2, and when you take mass 2, this will be x2 minus x1. Steady state response of 2 degree of freedom is assumed as x1 is capital X1 sine omega t plus phi and x2 is capital X2 sine omega t plus phi. The phase has been kept the same. The amplitude has been changed like in the previous experiment. By substituting x1 and x2 in the equation 1 and 2, you will get this equation 4. By solving the equations 3 and 4, amplitude of vibration of the main system and absorber system is given by x1 and x2. This is for the main system x1 and x2 is for the absorber system. From equation 5, it can be observed that the amplitude of vibration of main system x1 can be 0 if the numerator becomes k2 minus m2 omega square is 0. If this term becomes 0, this will become 0. So we can say that we are equating this term to 0 and omega square will become k2 upon m2, which will be equal to omega n2 square, which means we are equating it to the natural frequency of the body. From equation 7, it can be concluded that when the excitation frequency is equal to the natural frequency of the absorber, then main system amplitude becomes 0, which means you are trying to excite your absorber system such that it is reaching a frequency which is the natural frequency of the absorber, and it will in turn absorb the frequency from the main body and making that frequency of main body as 0. So this is the logic of dynamic vibration absorber, even though it is excited by the harmonic force. Dimensionless form of equation 5 and 6 is written here. I have already explained what is dimensionless form in the previous experiments. Please go through them. Equations 8 and 9 give the amplitude response of the main system and absorber system as a function of exciting frequency, where xst is f naught by k. xst is the zero frequency deflection of the main system. Omega 1 is the natural frequency of the main system. Omega 2 is the natural frequency of the absorber system. Omega is the frequency of external excitation. And mu is the ratio of absorber mass to the main mass. So these are certain terms defined here. Figure 5 shows the variation of x1 upon xst for different frequency ratios. So you can see here, when your frequency ratio is 1, this graph is reaching infinity. And for the rest of them, it is increasing exponentially and then decreasing with the use of absorber. Without the use of absorber, again this kind of a graph will be obtained, the red one. And with absorber, you will see this kind of a graph, the black one. And when there is a resonance, there is infinite frequency. And hence this displacement is showing infinity. Next, we will see the procedure. Set the value of primary mass and stiffness M1, K1. We have to set the value of both of them. Set the operating frequency at which you wish to operate the system. This omega is what we have to define. Edit the value of secondary mass and stiffness M2 and K2 such that the vibration in primary mass reduces. You can see here initially it was of this sort. When you changed M2 K2, this has got reduced. Right click arrow to observe the graph of x2 by xst. So this is another graph that you can obtain for the absorber part. So let's go to the self-evaluation tab. There are a few questions given here. You can just go through them, solve them. It is based on the theory that we have studied, so it's not very difficult. So here is the simulation tab. Let's set the value of omega. We can also set K1 and K2. You have to just click on edit K1, K2. So let's set the value of K1 and M1. You can see here it determines the amplitude of displacement shown in the graph. We can also change K2 and M2, and this is the graph of x1 upon xst. You can just change and check these values. If you click on this, you will get the graph of x2 upon xst. So you can just change the value of force. So you can increase the force and check out these graphs. You can change omega. So you can see here there is a difference in the graph obtained. So that's the simulation part. There is a simple assignment question. You can go through it. There is a quiz given here. You can just go through it. It's very simple. There's a video given here which explains about how to conduct the simulation experiment. There are a few references given. And finally, you have the feedback to share the experience of using the simulation. So with this, I end the session. I hope you have understood how to analyze the dynamic vibration absorber. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.